All right, so we're going to continue looking at section 5.4. Okay, it's part 2. And today we're going to start to get away from the more visual idea of vectors. We'll do a little visual, but we're going to get more into how can we just represent vectors with numbers and say add, subtract them without drawing the whole thing. Okay, because that's kind of time consuming. All right, so our first example is describing when two vectors are equal. Okay, so if you remember about this notation yesterday, this notation doesn't describe where to put the vector. All it tells you is that if you have a start point and you have an end point, how many left and right, how many up and down to get to the terminal point. But it doesn't necessarily tell you where you need to start from. So when we say two vectors are equal, it's not that the vectors are drawn in the same spot. That doesn't matter. Two vectors are equal if their x components match and their y components match. Okay, so here's an example. Here's a vector. And I'm going to take that same vector, I'm going to make a copy of it, but it's in a different spot. Those vectors are equal. They're not in the same spot, but they are equal. Okay? Another way of saying they're equal is they have the same magnitude and they have the same direction, but they don't have to start and stop at the same initial and terminal point. All right, any question on what it means for vectors to be equal? All right, how about if I did this? Are those two vectors equal? No, they're not equal, but what's different about them?
One's negative.
Yeah, one's the negative, which affects the direction. Okay. What is the same, though? Yeah, these each have the same magnitude. It's very easy to see. Okay. The vectors have the same magnitude, but different directions. So these are not equal vectors. All right. So we're going to look at a third way that we can write a vector. Okay, this will be our last way, and it's called unit vector notation. It's very, very similar to the way we learned yesterday using the angle brackets. But first, let's look at two special unit vectors. So for those that weren't here yesterday, a unit vector is basically just a vector that's 1 unit long. That's a unit vector. Right, so the vector I, okay, that's a special unit vector. It's 1 unit long, and this is going to be a unit vector that points to the right. Okay, points 1 unit right. Okay, we've got another vector, vector j. That's also going to be a unit vector. And that's going to be pointing up 1 unit. So I is a unit vector that points 1 unit right. J is a unit vector that points 1 unit up. And the idea is basically you can build any vector that you want by stacking together these i's and j's. Okay, you might need a certain amount of i's and a certain amount of j's, but I'll show you how to do it. Okay, stack them together and create a vector. Okay, so on the right-hand side, I've drawn a grid just showing I, 1 unit long, pointing to the right, and j, 1 unit long, pointing up. Okay, any questions what I or j are? Okay, remember, there's 2 ways you can abbreviate a vector if you're using a single letter. Either make the letter look bold, but that's kind of hard for me to continually do on the smartboard, or you can put a little arrow above the letter. Right? Either way, that symbol makes it a vector. Look. All right, so we're going to take these i's and j's and let's stack them together and see if we can make the vector 3, 4. All right, so 3, 4 would be right there. So let's draw in our vector. You know what? Let me make it different color so you can see the arrowhead. So there's our vector. Now I'm going to try to start stacking i's and j's together till I get to that point. Okay, so let's start with the i's. You know what? Let's do those in green. All right, so we got one I. How many i's am I going to need? Yeah, I'm going to need 3 of the i's, okay, to get over to where I want to be. So there's 2 and 1 more. 3. Okay, and that's actually the first part of how you can write this vector. It's 3i, but we need a little bit more. How many j's am I going to need? Yeah, I'm going to need 4 of those. Let's do those in a different color. It's kind of hard to see. That's it. All right, so we got 1j. Okay, take another one. That gives us 2j. Okay, we're almost there, halfway. Take one more. We're at 3, and we need 1 more. So what we basically did is we just built the vector 3, 4 using 3 i's and 4 of the j's. And that's another way to write the name of the vector, 3i plus 4j. You do not need the angle brackets if you're going to write it as ij. But if you're going to write it with a comma and you're not using I and j, you do need the angle brackets. Okay? Yeah?
So is it always going to be x with an I and 4 with an, and y with an J?
Yeah, I always represents your horizontal movement, and j represents vertical. Now, I and j, I could get anywhere I want in quadrant 1. Okay? Even decimals. If you wanted me to do 3.5, well, I could take I, scale it in half, and then I could add that on and do a half. But how about the other quadrants? How could I get to 2, 3, and 4 using i's and j's?
Negative.
Yeah, negatives. If I had negative I, instead of pointing right, that would point left. And then j, positive j is up. What about negative j? Down. So together, with using I and j, positive or negative, I can get anywhere I want in this plane. Okay? So what we say is these two vectors, I and j, they span, or they cover, the entire plane. If you get rid of one of them, let's say we get rid of j. If I just use i's, can I get everywhere I want to go on the plane? No. What am I stuck with if I just use i's? I'm stuck with left and right. I can never get up or down. Same if I just use j. All right? And then if we extended this to 3D, would I and j allow me to go anywhere that I want in 3D? No. With I and j, all I would be is stuck on this board. Think of 3D as coming out of the board and going behind the board. I'd need something else that allows me to go forward and back from the board. Okay? And that would be k. So we could have a unit vector k. We'll talk about that when we do 3D. Okay? So the idea is however many dimensions you have, you need that many vectors. 2D, 2 vectors. 3D, 3 vectors. For now, just 2D, I and j. Any question on that? All right, so we'll practice each notation. Okay, we'll do a little bit with unit vector and a little bit with the algebraic vector. It's good to know both. Okay, so here's some formulas for vectors. Okay, assume v and w in the following formulas. They will represent vectors. Alpha is going to represent a scalar. What does a scalar do to a vector? It makes it what? Yeah, change the size. Can make it longer, can make it shorter. Can a scalar do anything else besides change the size? It can. What else can it do? Yeah, it can change the direction if it was a what kind of number? Negative. Okay, so a scalar is just a number. Positive numbers will stretch your vector bigger. Numbers between 0 and 1, like fractions, 1/2, 1/3, they make it smaller. Negative numbers, they would make it larger or smaller, depending on the size, and flip the direction. Okay, so vector v, I wrote it as an algebraic vector. It's got a component of x1 and y1, horizontal, vertical. And vector w also has two components. x2 is the horizontal, y2 is the vertical. In an actual problem, those would be numbers. Okay, so there's our formula for how we add vectors. Okay, we don't have to sketch it and try to line up the terminal point and the initial point and all that stuff anymore. All we got to do, if you want to add two vectors, take the x components, add those up, comma, take the y components, and add those up. And that's it. No sketch needed. How do you think we do subtraction? Subtract the components, yeah. If you want to do v minus w, take x1 minus x2, comma, and then y1 minus y2. So much easier than having to take a vector, flip it around the other way, and then add the opposite. Okay, we don't have to do any of that sketching anymore. Right, so this is a scalar product. It's a number times a vector. Okay, to do a scalar product, all you have to do, it's almost like distributive property. Take the number that's in front of the vector and multiply it to each component. So if it was like a 2, I'd multiply the x component by 2 and the y component by 2. Right, and the last formula, what does this symbol mean? You get the double bars with a letter inside them. Not absolute value. It's similar, kind of.
Double F's.
Yeah, double absolute value. Well, if it depends, it could equal 1. It could actually be any number, but that's a hint. This is actually a number, and this number represents the what of the vector. It's the magnitude. Okay, so when you have the double bars, that symbol means magnitude. Could be 1, it could be 3, it could be anything. It could even be 0 if it was the 0 vector. Let's take a look at how we get the magnitude of v. Let's say that's v, and it's got two components. There's the horizontal and the vertical. Let's call the horizontal, that's the x1, that's y1. Right? And that's my vector. So x1 is going to represent the length from here to here. y1 is the length from here to here. If you knew x1 and y1, how would you find, not v, because we have v, that's drawn, but how would you find its length? Yeah, it's just the Pythagorean theorem. So you square x1, you square y1, you add them together, and then what's the last step in the Pythagorean theorem? Square root. Normally the other side would be squared, but if we solve for it, you take the square root. So there's the formula for the magnitude. Okay, same thing. So if you forget what the formula is, you can just really draw a triangle. We're going to be drawing a ton of triangles today. That's what everything really simplifies down to. Okay, triangles. Any questions on those 5 formulas? Add, subtract, scale, 4 formulas, sorry. All right. So let's try a couple different problems. Okay, let's try v plus w. First we'll write it with unit vectors, then we'll do it with the angle brackets. Okay, anyone think they could tell me what the I component will be when you add v to w? What would be the I component? Well, Evan, what do you think? What's the I component there?
That's the,
When you do v plus w?
5i.
Yeah, it's going to be 5i. And somebody else think they could tell me what the j component would be when you combine them together? Yeah.
Negative.
What is it? Negative?
Negative 1j.
Yeah, so you can write negative 1j or negative j. That's fine. Question?
How did you find that?
Can you explain which one, the 5 or the negative j?
Both.
Both? Evan, can you explain how did you get 5i?
You add the horizontal column together.
Yep, and what was the horizontal for v?
I.
2i.
2i.
And then for w?
3i.
So if you have 2i plus 3i, that's 5i. Okay, and then the same thing for j. 3j, take plus negative 4j. It's like 3 take away 4. Negative j. Someone else tell me, how about with the angle brackets? Yep. 5, negative 1. Okay, I will tell you the ij notation is used more. It is used more. All right, let's try, if we can keep that on the screen, v minus w. Okay, v minus w. Kayla, could you tell me what my I component would be for v minus w? Well, it's going to be a number in front and then an I. So if you look at what your number is for v, that's the 2i. For w, that's the 3i. And you're just subtracting. Sure, anyone help her out? Is that right?
Would it be negative I?
Negative I. Yeah, can you explain that?
You do 2i minus 3i.
Yeah, 2i minus 3i. So you're just following your formula for subtraction. Take the x components and subtract them, the horizontal. So in this case, the horizontal is 2i, the other one's 3i, and we subtract. How about j? Be careful with this one. Yeah?
7j.
Positive or negative? Yeah, positive 7j. Okay, the reason you have 3 take away negative 4. That becomes 3 plus 4. Right, and as an angle bracket, you could write negative 1, comma, 7. Right, 3v. Okay, what's that going to do to the vector? 3v. Yeah, it's going to make it 3 times. Okay, so we just said that that's going to take v and make it 3 times as long. So if you look at v, it's 2i plus 3j. What would the I component be if you triple it?
6i.
6i. How about the j component? 9j. Yep. And as an angle bracket? 6, comma 9. Okay? That's it. And D. Okay, D is the last one, finding the magnitude. Okay, when you find the magnitude, what's the first symbol you should write down so you don't forget to do it? Yeah, put down the whole thing is square rooted. Anybody tell me the 2 numbers that are going to go in under the square root? Yep, x1 and y1, which in this case is the 2 and the 3, and what do you have to do with each one of them? Square them. Right, you're just doing the Pythagorean Theorem. 2 squared is 4, 3 squared is 9, 4 plus 9, 13. And that's it. If that could be reduced, I would reduce it. For example, if you got square root 16, you could do it. If you got square root 20, you could also break something like that down.
So it's going to be one answer, not a point.
Be careful. I was just going to mention that. It is going to be a single number, not a... What were these other answers? These are not coordinates. Coordinates look like this. These are vectors. Right. Okay? So when you find a magnitude, it's different than everything else. Scaling, the answer is a vector. Subtracting vectors, you get a vector. Adding vectors, you get a vector. Finding the length of a vector, number. It's just a number. Okay, so that answer is a little different than the other three. Okay, any questions on that? Okay. So remember what we said about a unit vector? Okay, a unit vector is a vector that is 1 unit long. Now we've got 2 special unit vectors. I always points right. J points up. I'm just drawing a vector on an angle. So this isn't I or J, just generic vector. Okay. And let's suppose that we had that vector in black. Right? And that it's more than 1 unit long. Okay. What I'm going to try to do is I want to find a unit vector, basically like the one in red. It's still going to point exactly the same direction as the black one, except I want to make it so it's 1 unit long. So that's what I'm going to try to do next. We're going to be given a vector. It's going to be pointing in a certain direction. And we're going to try to find a new vector. It's still going to point the same way. We're just going to change the length of it. And we're going to change the length so it's exactly 1 unit long. Okay, so let's see if we can come up with a way to figure that out. And the easiest way might be to start with an example with numbers. And then kind of work backwards and think about it. Okay, let's pretend that vector in black, I'm just going to make up a length for it. Let's say that it's 5 units long. If it's 5 units long, is it a unit vector? No. How long does it have to be a unit vector? 1. So we want to somehow change it so that it's 1 unit long. Yeah, basically if you scale it, right, divide it by 5. Okay. So divide by 5. If you have a 5 unit long vector and you divide by 5, it'll make it a unit vector. Okay. What if you had a vector 8 units long? How would you make it 1 unit? Okay, divide by 8. Okay, I'll do one more. Okay, what if you had one 12 units long? To make it 1 unit, divide by 12. So all you're doing is you're basically taking your vector and dividing by what? The number that represents what? Yeah, the magnitude, exactly. So all you have to do to find a unit vector is take your vector and divide by whatever its magnitude is. That's exactly what the formula is. To find a unit vector, take your vector and divide by its magnitude. Now, if the magnitude already is 1, well, you're done. It already is a unit vector. If it's not 1, you'll find the length using the formula we just had on the other page and plug into the equation you see right here. Okay, so here's a vector. 3i minus 4j. So it's 3 units right, 4 units down. Do you think if you sketch that starting at the origin, and you went 3 units right and 4 units down, would that be a 1 unit long vector? No. Okay, so first thing is, let's find out how long is it. Okay. Once we figure that out, then we can divide this vector by its magnitude, and that'll change it into a unit vector. Okay, what are the two numbers that get plugged in under the root? Yeah, x1 and y1. So in this case, what's x1?
3.
Yeah, 3. And y1? Negative 4. What do we do with each one of those? Square them. Okay. What's 3 squared? 9. What's negative 4 squared?
16.
What do you get when you add 9 and 16? 25. So how long is vector v? 5 units. Okay, so that tells us the length. So let's take our vector and divide by its length. Okay, the way we do that, take 3i minus 4j and divide each component by its length. So you didn't change the direction at all. All you did was scale the vector. You basically multiplied each component by 1/5. You could think of it that way. So that's it, 3/5. Usually we put the letter more in the middle, but that's fine. So it's 3/5 I minus 4/5 j. Okay, any question on that? That's how you find a unit vector. So unit vectors are helpful if for some reason the magnitude isn't important and all you care about is direction. It's a lot easier to work with something that's a length of 1 rather than, say, a length of 5. 1 is just easier to do arithmetic with. All right, and the last two things we'll do are the applications. So the first one is going to be what's called a velocity vector. Okay, so a velocity vector is going to represent two things, okay, because it's a vector. And the two things you represent are the direction and the speed. Okay? So this would be an example where we're going to throw an object. Okay? We're going to throw an object. We're going to throw it at a certain angle. And we're going to throw it at a certain speed. So let's see if we can come up with the formula, okay, for a velocity vector. Okay, let's say that this vector represents somebody throwing a baseball. Okay, to simplify the problem, this is really a simplification, but let's assume that the ball goes straight. When somebody throws an object, though, up at an angle, does it really go straight? No, it curves. Because the second it leaves your hand, gravity's pulling it back down. Right, but just makes it easier. Okay, what shape do you think I could make out of this picture that would help us figure out horizontal and vertical stuff? Yeah, let's make a triangle. Okay, so we've got two components here. This object has a horizontal component and a vertical component. Do the vertical component in red, and then, horizontal in red, and the other one in blue. Right. Now, this part here would represent the ground. Okay? This black line up at an angle, that's like the hypotenuse. That's the angle you're throwing it at. Let's call that angle alpha. Okay, and let's give names to our horizontal, the red vector, and the vertical. We'll call that the blue vector. And I used x and y to name them. All right, so my goal is to figure out a formula, because they're going to give me the angle in the problem. They're going to give me how fast I throw it. And my goal is to figure out x and y. So somehow I'm going to use that piece of information, that piece of information, and that piece of information. So which trig function would involve x here? Which trig function would involve x, and it's also going to involve the hypotenuse? Yeah, cosine. So you take the cosine of your angle, that's equal to adjacent. And now x, I'm letting represent that length. Y, that length. Now v isn't the length, that's the vector. How do I represent the length of v? The double, yeah, the two bars. Okay. So the cosine of our angle equals adjacent over hypotenuse, specifically the length of the hypotenuse, not the direction of it. I don't care about the direction. The angle takes care of the direction part. Right? And now I want to get x by itself. So how would I get magnitude of v on the other side? Hey, you multiply. Magnitude v, cosine alpha. And just by kind of looking at the pattern, anybody have an idea what the formula for y would be? Think about a trig function that would involve the angle. Let's do it in a different color. The angle, the hypotenuse, and the y. Sine. So what would be my formula for y, you think? Yeah. And you can go through all the trig ratio again. Cosine is opposite over hypotenuse. Solve it for y, and you're going to get that. Okay, so this is your horizontal component, and below is your vertical. So now we can write a velocity vector. All you need are the two components. So first one, magnitude v, cosine alpha, magnitude v, sine alpha. Okay, but as I said before, the angle bracket notation isn't used as much. So instead, let's write it with I and j. Okay, it's almost the same thing. Put I, and then put your horizontal component in front of it. Magnitude v, cosine alpha. Okay, in the second part, put j, and then put your vertical component. Magnitude v, sine alpha. Okay, all these are the formulas for the two sides in a right triangle, using right triangle trig. And this last one we can actually simplify. We can make it look a little bit simpler than that. What do both parts have in common? The magnitude of v. So what can you do when two things have something in common? We can't cancel it, but we can factor it out. Just reverse the distributive property. Put it on the outside. That way, we only have to write it once instead of twice. And this is the formula for a velocity vector. Right. They'll give us the speed we throw it at. That's the magnitude of your vector. And they'll give you the angle you're throwing it at. We basically just have to fill in that formula. So that's the same thing you just had on the other page. Okay, so all you really need to know is that alpha is the angle you're going to throw the object at. And then your initial velocity. Oops. That's the magnitude of v. Okay, just make sure you have that formula copied down with those two things. That's all you need. Okay, any questions on that formula? Okay, so this is the simple application, because all we have to do is fill in a number for alpha, fill in a number for magnitude v, and then type it into our calculator. There's not really a lot of thinking we have to do. Just make sure everybody's got the formula. You got it? Okay. So it says we're going to throw an object 50 miles per hour at 30 degrees. That's all we really need to know. So we'll find the velocity vector. We'll write our answer as a unit vector with I and j. And then I want to explain the meaning of each component, okay, in terms of the real-world application to this. Okay, somebody give me, what's my formula that the last one we had? It's magnitude of v. In parentheses, what comes next? Cosine alpha, and then I. Sine alpha, and j. Okay, what's the magnitude of my vector? How fast am I throwing the object? 50. So make that 50. What's the angle? 30. So change alpha to 30. Sine 30. Okay. Now we just type it in. See what we get. Which property do we use to simplify a number on the outside of parentheses? Yep, that's a distributive. So let me do cosine of 30 times 50. So we get 43.3 I. And now do sine of 30 times 50. So sine of 30 is a half times 50, 25. So we get plus 25j. So there's a velocity vector, and we wrote it the way they wanted, unit vector form. Now, I want to know what each of those numbers mean. Okay, I want to know what the 43.3 means, and I want to know what the 25 means. In terms of if you actually threw this object, the 43.3 describes something about the object, and then the 25 describes something else about the object. Well, this is a velocity vector, so everything that you see here has to do with speed or velocity. Can you be more specific? You're on the right track. More specific than how fast it's going. So I know the object is traveling 50 miles per hour at a 30-degree angle, but this 43.3 means something else. Yep.
It's going 43.3 miles per hour horizontally and 25 miles per hour upward. You are you're all
So if somebody was standing, say, 200 feet away from you, and you threw this object, assuming it didn't hit the ground before you threw it hard enough, we'd have to figure out how far it's really going to go. But the object would be coming at the person at 43 miles per hour, roughly. It's not coming at them at 50, because you didn't throw it straight at them. You threw it up a little bit. Okay? If you threw it straight at them, it would get there faster. Kind of like a line drive or something in baseball. Okay? If you hit it straight, it's going to go faster. If you throw something very high, it's going to take a longer time to get where it's going. Okay? And then this is the vertical speed. And these two speeds are completely separate of each other. The only thing that controls them is the angle you released it at and gravity. Which speed does gravity affect? It only affects one of them.
Vertical.
Yep, the vertical. Horizontal speed would be affected a little bit. Anybody know what would affect the horizontal speed as something moves through?
Air.
Air. Okay, so air resistance would slow down the object horizontally. Okay? And I guess it would affect it vertically a little bit too. But gravity has nothing to do with 43.3. Okay? If there were no air where you threw this object, well, you wouldn't be breathing. But besides that, 43.3 would stay the same the entire time. Vertical speed, the second that ball leaves your hand, it's not going 25 miles an hour anymore. Gravity's already slowing it down. Okay? Until it reaches a vertical speed of 0. And that's when it would be at its highest point, and it comes back down. So we could figure out all kinds of things. How high does this ball go? How far does it go? Say we got a wall 100 feet away that's 12 feet high. Is it going to clear the wall? All kinds of physics stuff. We're not going to get into that, but I just want you to understand how to find a velocity vector and what each component means. Hey, any questions on that application? All right. So the next application. Okay, so next one's a little bit harder. It's called static equilibrium. What does it mean if something's in equilibrium? Anybody know what that means?
Balanced.
Balanced. Okay? And static, if you think of static means it's not moving. Okay, so we're talking about something where everything is nice and balanced and it's not moving. Okay? An example of static equilibrium is the pile of papers on that table. Gravity's trying to pull those papers down. But there's something else that's pushing up on the pile of papers. The table. The table's holding them up. So they're balanced. Okay? If there was no table under the papers, they'd be falling because the forces wouldn't be balanced. Gravity would pull down, but there'd be nothing to counteract gravity. Right? So an object is in static equilibrium if the sum of all the forces acting on it is 0. Okay, another example where you might see this, think of a tug of war. Okay, we used that yesterday, I think. Imagine that one team is pulling with 10,000 newtons of force to the left, and the other team is pulling with 10,000 newtons of force to the right. Well, the rope's not going to move. If each team is pulling with the exact same amount of force left and right, it's going to be in static equilibrium. If one team starts to pull harder than the other team, then the forces become unbalanced, and it's going to move in that direction. Okay, so what we're going to look at is an object that weighs a certain amount of weight being suspended by 2 cables. Okay, just like that. And I want to find the tension in each cable. So kind of the big overview here is we got to understand that this is in static equilibrium and figure out what that means. Then we're going to use a little bit of right triangle trig. And then we're going to also look at how do we solve a system of equations. So there's some stuff in here that you already have to know from Algebra 1. The right triangle trig goes back to what I taught you. And the static equilibrium part, well, we're learning that right now. Okay, so first thing I want to do is I want to make some triangles in this picture. Okay, so what I'm going to do is draw a line about like that. Draw one like that. And one like that. Okay, so I just created 2 different right triangles. Now, in the problem, you can tell that the 2 ropes holding up the weight, they're different lengths. All right, so you know what? Let me make the lines we added. I'll put those in red so you don't get confused. The black lines are the cables. All right, and they want us to find the tension in each cable. So let's call this cable in black, think of it as a vector. Okay? It's pulling. Well, actually, can somebody tell me, what direction is this black cable pulling in? It's holding up that weight. So which way is it pulling? It's pulling up, but what way is it also pulling? So it's definitely pulling up, otherwise it'd be falling. But what else? Somebody said it's pulling. It's pulling to the left. Think about what would happen if you cut this other cable. which way would this weight all of a sudden swing? Left, because the cable's pulling left, right? So there's two components. We have a component, let's do it this way, pulling left, and we also have a component, I'll do it in blue, pulling up. So this cable is pulling left and up. How about the other cable?
Right, and then
Yeah. Think about what would happen if you cut this other cable. All of a sudden, the 1,200 pounds would swing to the right. That's because this cable is pulling right, and it's pulling up. Okay, so here's the up, and the other part is right. Okay, and we're trying to find the tension. Okay, so we just said that the black cable is pulling left and up. Let's call the tension in that cable T1. Think of that as the magnitude of the vector. How long is this black vector? That's the tension. Okay. The direction? Well, that's all these angles everywhere. All right, and what else? Let's call this other cable T2. Think of T2 as the length or the magnitude of the cable. Okay? That's the tension in it. How long is it? The angle, that's the direction. Okay, let's fill in a few other angles. If this angle is 30, how about the one next to it? Yep, that's a 60. How about the one down at the bottom? That's also a 30. Another way to figure out that these are 30s is you have two parallel lines cut by a transversal. The alternate interior angles are equal. So if you like the geometry part, you can look at it that way. I like looking at it as the angles add up to 180 in a triangle. Either way. How about this angle down here? It's also going to be 45 for the same reasons. Okay, so now we've set up our diagram and we've added everything we're going to need to add to it. Now we have to describe that. What are the different ways that this 1,200 pounds could try to move?
Someone trying to push it.
So what would be the directions it could move in? It could move left and right. Is it moving left and right? No, it's not moving left and right. So what does that mean? If it's not moving left and right, the force acting left and the force acting right must be what?
Equal.
It must be equal. If they weren't equal, it would be in motion. So the force left equals the force right. Eventually, we got to change that into an equation involving our angles. And what's another way this could move besides left and right?
Up or down.
It could be moving up or down. Is it moving up or down? Nope. So that means the force pulling up and the force pulling down are the same. Right, we don't have labels for those forces yet, the blue and the red lines, so let's just give them names. Let's call the vertical forces Y1 and Y2. And what do you think a good name for the horizontal forces would be? Yep, X1, X2. So I got all the 2's in one triangle, I got all the 1's in another one. Okay, any question on the diagram or the setup so far? These two equations are going to be the key to the whole problem. This is the part you have to understand. Now we're going to start to get into the trig part. Okay, the physics part, that's that. Now let's see if we can get out and get into trig. Okay, what's the force going left in this picture? X1, that's the only force that's going left. So X1 has to equal, what's the force going right? X2. Now this is great that we put X's and Y's in here. Eventually we want to talk about the tensions in the black cables. Okay? Because remember, the red and the blue don't really exist. We added them in to create triangles that are going to help us, but they're not really there in real life. The T1 and the T2 is all that's there. Okay? But that's a good start. Okay, what about force up? Y1. What else?
Equals Y2.
So how many forces are up in this case? There's 2 forces. Each cable is helping to hold it up. So Y1, that's a force up. Y2, that's a force up. And they're working together.
So, Y1 times what or
Plus. It's kind of like if I pulled up with 50 pounds of force and you pulled up with 50 pounds of force, together we're pulling up with 100 pounds of force, lifting it. Okay, so total force up. What's the force down?
The 1,200 pounds.
1,200 pounds. That's because of gravity. So that's trying to come down. But it's not because it's being held up. Okay, any question on that? So now we're starting to get our equations and get some triangles in here. Okay, now we're going to do right triangle trig. We're going to do it 4 times. So if you start to see the pattern, we don't need to keep going through it, but let's start with x1. Okay, our goal is to write x1 using that angle and t1. We've got to get the tensions involved, because that's the real problem. So which trig function would involve x1 and the hypotenuse, which is t1? Cosine. Okay, so off to the side, write down cosine 30. Which side is adjacent? x1. What side is the hypotenuse? t1. And now solve it for t1. How would you do that?
Multiply x out.
Oh, solve it for x1, I'm sorry. Yeah, multiply it by t1. Okay, so we get t1 cosine 30 equals x. Any question on that? We're going to do that four times. We just did it once. Okay, so it's not hard, but it is very repetitive. Okay? All right. How about let's do our x's at the same time. Let's do the other x. Okay. What would be a trig function that would involve the angle, the x2, and the hypotenuse, t2? Cosine again. Cosine 45. What side is adjacent to the 45? x2. And what's the hypotenuse? t2. And again, how would I get the t2 on the other side? Multiply by t2. So now we got a formula for x2. It's t2 cosine 45. Right? So we got formulas for the x's. Let's look at the y's. Which trig function do you think we're going to use for both y's? We're going to use sine. Can I just write the formula, or does anyone need me to see the steps on how you get it? Yes, yeah? So you're thinking now, which trig function is going to involve 30, y1, and t1? That's sine. So the sine of 30 equals, what side is opposite 30? y1. What's the hypotenuse? Over t1. Same question again. How do I get t1 on the other side? Multiply. So t1 sine 30 equals y1. And if you look at the difference between y1 and x1, it's just the trig function you use. So that's going to be the same difference between y2 and x2. Anyone think they could just see the pattern now and tell me what y2 is? t2 sine 45. Yep. Now we're done the trig part. Okay, that's the entire trig part. Now we're just going to take our equations and we're going to substitute in. Plug that in for x2. Plug that in for x1. Plug that in for y1. Plug that in for y2. And then we're going to have a system of equations. And then that's where the algebra part comes in. Right? It's a lot of little things all put together, a lot of easy things. You just have to remember how to do them. So x1, it's t1 cosine 30. x2, t2 cosine 45. Okay, y1, let's see, that's t1 sine 30. Plus, let's see, y2, that's t2 sine 45. And don't forget what it's equal to, the weight, 1,200 pounds. Now the equation we have here, it's exactly the same as the equation we talked about earlier. It's just like you've got two different letters, and you've got numbers next to those letters. Okay, so what could I do? You know what? Let's just move the top equation a little further away. Okay, what can I do with that top equation that'll help me solve this system?
You can get T1 to one side, you can then make separate equation for the T2 to the other side.
Sure, we could get T1 by itself. Let's do it that way. How would you get T1 alone? Divide by cosine 30. Divide by cosine 30. That's gone. Now you've got a formula right here for T1. So once you find T2, all you have to do is plug it in. But let's find T1. So what happens? T1 is equal to T2 cosine 45. You solved for T1, plug T1 into the other equation. So you get T2 cosine 45 over cosine 30. And now just write out the rest of it. Sine 30 plus T2 sine 45 equals 1,200. And once we type in all those trig functions, the equation's going to look a lot simpler. Take the cosine of 45, divide by the cosine of 30, times the sine of 30. We'll go 0.41. T2 plus, let's do the sine of 45. It's 0.71 equals 1,200. Are those like terms? 0.41 T2 plus 0.71 T2?
No.
Yep, just add them up. 0.41 plus 0.71. 1.12 T2. And how do I get T2 by itself? Yeah. Divide by 1.12. Yep, it is. So you got 1,200 divided by 1.12. So the tension in one of the cables is 1,071.4 pounds. And now you've got that number. You could plug it right in to find T1. Now, remember, you can't subtract that from 1,200. The reason is, think of a tug of war. Maybe your rope weighs 40 pounds. There could be 10,000 pounds of tension in that rope, though. If each person is each team pulling really hard, the weight doesn't necessarily limit the tension. Okay? You could have 10,000 pounds of tension in a tug of war rope, even though it only weighs 20 pounds.
What's that say?
That's T2.
No, what does the answer say?
1,071.4.
Oh, okay.
And then to find T1, just fill that number in right there and multiply it on your calculator. Okay, so we'll go through another one of those tomorrow. But I think if you watch the steps again slowly, it'll make sense. Okay, so the homework is on page 344. It's 25 to 47 odd, 55, 57, and 66. Okay, so just odds on 25 to 47.